Welcome. I want you to do something for me right now. Just settle in. Get comfortable. Adjust your pillow. Pull your blanket up a little higher. Take a slow breath in and let it out. Good, because tonight we are going on a journey together. A slow, deep, beautiful journey through one of the most fascinating subjects in all of human knowledge. We are going to talk about geometry. But wait, before you think this is going to be some boring classroom lecture with a teacher drawing triangles on a chalkboard, let me stop you right there. This is nothing like that. Not even close. Tonight, I am going to show you that geometry is not just some subject you studied in school and forgot about. Geometry is literally everything. It is the hidden language of the universe. It is the secret code running through your body right now as you lie there listening to me. It is the reason stars form, the reason flowers bloom, the reason your heart beats, and the reason galaxies spin in the vast emptiness of space. And I am going to explain all of it to you slowly, calmly, in a way that lets your mind wander through these incredible ideas while your body relaxes deeper and deeper into rest. Let me start by blowing your mind with a few things. Right now, inside your body, there is a molecule called DNA. You have heard of it. It carries all the instructions for making you who you are. And the shape of that molecule is a geometric spiral, a double helix. Two intertwined spirals twisting around each other with precise geometric angles. And here's the crazy part. If you took all the DNA from every cell in your body and stretched it out end to end, it would reach from Earth to Pluto and back, multiple times. All of that information, all of that length, packed into your body using the power of geometric folding. That is geometry keeping you alive right now. Here's another one. NASA sends spacecraft to other planets millions of kilometers away. And to do that, they use geometry so precise that a mistake of 1/1000th of a degree in their calculations could send a spacecraft thousands of kilometers off course. Think about that. The difference between reaching Mars and drifting into the void of space forever comes down to geometry. Angles, curves, shapes, the same basic concepts that ancient humans first scratched into cave walls tens of thousands of years ago. And speaking of ancient humans, here is something that will really get you. The ancient Egyptians built the Great Pyramid of Giza over 4,500 years ago. No computers, no calculators, no laser measuring tools. And yet, the base of that pyramid is level to within just a few centimeters over a distance of 230 meters. The sides are aligned to true north with an accuracy of 3/60ths of a degree. Modern engineers with all our technology would struggle to match that precision. How did they do it? Geometry. Pure, beautiful geometry passed down through generations of brilliant minds. So tonight, we are going to explore all of this and so much more. We are going to start with what geometry actually is, not the boring textbook definition, but the real, deep, philosophical truth about what geometry means. Then we are going to look inside your own body and discover the incredible geometric structures that keep you alive. We will travel back thousands of years to ancient civilizations and see how they used geometry to build wonders of the world. We will explore the patterns of nature, the spirals and hexagons and fractals that appear everywhere from sunflower seeds to hurricane clouds to the arms of galaxies. We will venture into space and discover how geometry governs the orbits of planets, the shape of space-time itself, and the terrifying geometry of black holes. We will look at how geometry affects your brain and your sleep. We will dive into the mind-bending world of fractals, where infinity hides inside finite shapes. We will bend the rules of geometry itself and explore what happens when straight lines curve. And we will look into the future, where geometry meets artificial intelligence and quantum computing and the exploration of other worlds. All of this, slowly, calmly, with wonder and curiosity. So if you are lying in bed right now, or you have had a long, exhausting day, just let yourself relax. Hit the like button so this video can help others find this calm too. Subscribe if you want more of these deep, peaceful explorations. And in the comments, tell me something. What shape do you find the most beautiful? A circle? A spiral? A star? Something else? I genuinely want to know. Now take another slow breath and let us begin. So what is geometry? Really, what is it? If you ask most people, they will say something like, oh, it is the study of shapes, triangles, circles, squares, that kind of thing. And sure, that is part of it. But that is like saying music is just sounds, or that the ocean is just water. Technically true, but it misses everything that makes it profound. The word geometry comes from ancient Greek. Geo means earth, and metron means measurement. So geometry literally means measuring the earth. And that is how it started, thousands and thousands of years ago, when early humans needed to measure their land, figure out where to plant crops, and understand the world around them. But geometry quickly became so much more than measuring fields. It became the language that humans use to describe the fundamental structure of reality itself. Think about it this way. Everything around you has a shape. The screen you might be looking at, the room you are in, the curve of your pillow, the arc of the moon outside your window, the spiral of your ear, the sphere of your eye. Every single physical thing in the universe has a geometric form. And the relationships between those forms, the angles, the proportions, the symmetries, that is what geometry studies. It is not just about shapes. It is about how shapes relate to each other, how they fit together, how they create the structures we see at every scale, from atoms to galaxies. There is a beautiful quote attributed to Galileo Galilei, who said that the universe is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. And the more we have learned about the universe in the centuries since Galileo, the more true this has proven to be. Geometry is not just a tool we invented to solve problems. It is the operating system of reality. Now let us start from the very beginning. The absolute foundation. Geometry is built on three fundamental concepts: a point, a line, and a plane. These are so simple they almost seem trivial, but they are actually quite profound when you think about them slowly. A point. Imagine a single star in a completely dark sky. No other stars, no moon, no anything. Just one tiny dot of light in infinite darkness. That is a point. It has no size, no width, no height, no depth. It is just a location, a position in space, nothing more. You cannot measure a point because there is nothing to measure. It is the simplest possible geometric concept. And yet, everything in geometry is built from points. Every line, every shape, every curve, every three-dimensional structure you can imagine is ultimately made up of points. Now imagine a second star appears in that dark sky. And imagine a beam of light connecting those two stars, stretching perfectly straight from one to the other, and then extending infinitely in both directions beyond them. That is a line. A line has no width, no thickness. It is one-dimensional. It extends forever in both directions. And here is something interesting. Between any 2 points, there is exactly one straight line. This seems obvious, but it is actually one of the fundamental truths of Euclidean geometry. And as we will discover later, in other types of geometry, this is not always true. But for now, just picture that beam of light stretching infinitely between those two stars and beyond. And now, a plane. Imagine the surface of a perfectly calm ocean at night, stretching out in every direction as far as you can see and beyond. Perfectly flat, perfectly smooth, extending infinitely in length and width, but with no thickness at all. That is a plane, a two-dimensional surface. And on this surface, you can draw all the shapes you learned about in school: triangles, squares, circles, pentagons, hexagons, and infinitely many more. These three concepts, point, line, and plane, are the atoms of geometry. Everything else is built from them. And the person who first organized these ideas into a complete, logical system was a man named Euclid. Euclid lived in Alexandria, Egypt, around 300 BC. And he wrote a book. Well, actually, he wrote 13 books, collectively called the Elements. And these 13 books became one of the most influential works in the entire history of human civilization. For almost 2,000 years, Euclid's Elements was the second most printed book in the Western world, after only the Bible. Think about that. A book about geometry, printed and studied more than almost any other book in existence for 2 millennia. What made the Elements so special was not just the geometry itself, but the method. Euclid started with a small set of definitions and 5 basic assumptions, which he called postulates. And from those 5 postulates, using pure logical reasoning, he built up the entire edifice of geometry. Theorem after theorem, proof after proof, each one following logically from what came before. It was one of the first and greatest examples of what we now call the axiomatic method, building knowledge from basic assumptions using logic alone. And this method influenced not just mathematics, but science, philosophy, and even politics for thousands of years. Euclid's 5 postulates are worth knowing, because they are the foundation of the geometry most of us learn in school. And later, we will see what happens when we change them. The first postulate says that between any 2 points, you can draw a straight line. Simple enough. The second says that a straight line can be extended infinitely in both directions. Also straightforward. The third says that given any point in any distance, you can draw a circle with that point as its center, and that distance as its radius. The fourth says that all right angles are equal to each other. And the fifth, the famous parallel postulate, says that if a line crosses 2 other lines and the interior angles on one side add up to less than 180 degrees, then those 2 lines will eventually meet on that side. This fifth postulate might sound complicated, but it is essentially saying that through any point not on a given line, there is exactly one line parallel to the given line. And this seemingly simple statement turned out to be one of the most important and controversial ideas in all of mathematics. But we will get to that later in our journey. Now here is what is important to understand. Euclid did not invent geometry. People had been using geometric ideas for thousands of years before him. What Euclid did was organize it, systematize it, and prove it using logic. Before Euclid, geometry was a collection of useful rules and observations. After Euclid, it was a rigorous logical system, and that system has been the foundation of mathematical thinking ever since. But geometry is much, much older than Euclid. Let us go even further back. Evidence of geometric thinking goes back at least 40,000 years. Cave paintings from the Upper Paleolithic period show geometric patterns, dots, lines, grids, zigzags, and spirals. Stone Age tools show remarkable symmetry, with hand axes shaped into precise bilateral forms. These ancient humans did not have the vocabulary of geometry, but they clearly had the intuition. They could see patterns. They could see symmetry. They could create shapes with intention and precision. Why? Because the human brain is fundamentally a pattern recognition machine. Evolution shaped our brains to detect geometric regularities in the environment. Recognizing the symmetry of a face helps you identify friends and threats. Recognizing the pattern of a trail helps you find food and water. Recognizing the geometric regularity of a spider's web or a honeycomb tells you something important about the world. Geometry is not just something we learned. It is something our brains are literally built to perceive. And this, as we will discover later, is deeply connected to why geometric patterns can help you relax and fall asleep. So geometry has been with us from the very beginning of human consciousness. But it is not just in our minds, it is in our bodies. And this is where things get really fascinating. Let me take you on a tour of the geometry inside you right now. As you lie there, relaxed and still, your body is a symphony of geometric structures working in perfect harmony to keep you alive. And most people never think about this. Most people have no idea how much geometry is operating inside them at this very moment. Let us start with the most famous geometric structure in your body, the one I mentioned at the beginning, your Dina. In 1953, two scientists named James Watson and Francis Crick, building on the crucial X-ray crystallography work of Rosalind Franklin and Maurice Wilkins, discovered the structure of Dina. And what they found was breathtaking. Dina is a double helix, two long strands of nucleotides wound around each other in a spiral. But this is not just any spiral. It is a geometrically precise spiral, with specific, repeatable measurements. Each base pair is connected with a twist of 36 degrees. That means it takes exactly 10 base pairs to complete one full 360-degree turn of the helix. The width of the Dina molecule is precisely 2 nanometers. The distance between each base pair along the axis is 0.34 nanometers. These are not approximate numbers. They are exact geometric specifications, like the blueprints for a building. And in a sense, they are blueprints. They are the blueprints for you. The geometry of Dina is not just elegant, it is functional. The double helix shape allows the molecule to be incredibly compact. Remember, you have about 3 billion base pairs in each cell, and the total length of Dina in a single cell, if stretched out, would be about 2 meters. But it is all coiled and folded into a cell nucleus that is about 6 micrometers across. That is like packing 30 kilometers of string into a tennis ball. And the way it packs so efficiently is through multiple levels of geometric coiling. The Dina helix wraps around proteins called histones, forming structures called nucleosomes that look like beads on a string. These then coil into a solenoid structure, which further loops and coils into chromatin fibers, which eventually form the chromosomes you might remember from biology class. Each level of coiling is a geometric transformation. Spirals within spirals within spirals. It is geometry all the way down. And here is the health connection that matters. When the geometry of Dina goes wrong, when the precise angles and distances are disrupted, when the coiling does not work properly, that is when mutations happen. And mutations can lead to diseases. Cancer, for example, often starts when the geometric machinery that copies Dina makes a mistake. The enzymes that read and duplicate Dina depend on the geometry being perfect. A misalignment, a wrong angle, a structural error, and suddenly a gene is not copied correctly. The wrong protein is made, and a cell starts growing out of control. So in a very real sense, your health depends on the geometric precision of molecular machinery operating at the nanometer scale inside every single one of your trillions of cells. Now let us zoom out from Dina and look at the cells themselves. Your body is made of approximately 37 trillion cells, and these cells are not randomly shaped. Their geometry is carefully optimized for their function. Red blood cells, for example, have a very specific shape. They are biconcave discs. Imagine a disc that is slightly pinched in the middle on both sides, like a donut, but without the hole. This shape gives them a very high surface area relative to their volume, which is crucial because their job is to carry oxygen, and oxygen needs to diffuse across the cell membrane. A sphere would have less surface area for the same volume. The biconcave disc shape gives a red blood cell about 20 to 30% more surface area than a sphere of the same volume. And this extra surface area means more oxygen exchange. If your red blood cells were any other shape, you would not get enough oxygen, and you would not survive. Your life depends on the geometry of a tiny disc 7 micrometers across. White blood cells have a different geometry because they have a different job. They need to be flexible, to squeeze through gaps between other cells to reach sites of infection. So they are more spherical and deformable. Nerve cells, neurons, have yet another geometry. Long, thin projections called axons that can extend up to a meter in length, perfect for transmitting electrical signals across your body. Muscle cells are long and cylindrical, arranged in parallel bundles, a geometric arrangement optimized for contraction and force generation. Every cell type has a geometry that matches its function. This is not coincidence. It is evolution optimizing geometric forms over billions of years. Now let us go inside these cells and look at something remarkable. The cytoskeleton. This is a network of protein filaments inside each cell that gives the cell its shape and structure. And the geometry of the cytoskeleton is stunning. It is made of 3 types of filaments: microfilaments, intermediate filaments, and microtubules. Microtubules are hollow cylinders made of a protein called tubulin, and they are arranged in a very specific geometric pattern. 13 protofilaments arranged in a circle to form the tube. Why 13? This is still debated. But the geometric properties of this 13-fold arrangement seem to provide the optimal balance of flexibility and rigidity. Microtubules serve as tracks along which motor proteins carry cargo through the cell. They are the highways of the cellular transport system. And they are pure geometry. Let me take you somewhere really beautiful now. Your lungs. Take a slow breath in right now. Feel your chest expand. What is happening inside is a masterpiece of geometric engineering. Your lungs contain a branching network of airways called the bronchial tree. Starting from your trachea, the airway splits into 2 bronchi. Each bronchus splits into smaller bronchi. Each of those splits again, and again, and again. About 23 levels of branching in total, and this branching pattern follows fractal geometry. We will talk much more about fractals later, but for now, just know that a fractal is a pattern that looks similar at different scales. If you zoom in on a branch of the bronchial tree, it looks like a smaller version of the whole tree. This self-similar branching pattern is incredibly efficient. It allows your lungs to have a total internal surface area of about 70 square meters. That is roughly the size of half a tennis court, packed inside your chest. The only way to fit that much surface area into such a small volume is through fractal geometric folding. And all that surface area is necessary, because oxygen needs to diffuse across it into your bloodstream. If your lungs were just two simple bags without this fractal branching, they would need to be enormous to provide the same oxygen exchange. The fractal geometry of your lungs is literally what makes breathing possible. And the same fractal geometry appears in your circulatory system. Your heart pumps blood through your aorta, which branches into arteries, which branch into smaller arteries, which branch into arterioles, which branch into capillaries. The total length of all the blood vessels in your body is estimated at about 100,000 kilometers. That is enough to wrap around the Earth 2.5 times, all packed inside your body through fractal branching. And those tiny capillaries, the smallest blood vessels, are so thin that red blood cells have to squeeze through them one at a time, deforming their biconcave disc shape to fit through channels even narrower than they are. Geometry at every scale, from the shape of the vessel network to the shape of individual cells. Now let me tell you something fascinating about your heart itself. Your heart is not just a simple pump. It is a geometrically sophisticated organ with a spiral structure. The muscle fibers of the heart are arranged in a helical pattern, spiraling around the chambers. When the heart contracts, this helical arrangement creates a ringing motion, like wringing out a towel. This twisting action is much more efficient at pumping blood than a simple squeezing motion would be. The geometry of the muscle fiber arrangement is what makes your heart an efficient pump, and cardiologists actually study this geometry to diagnose heart problems. Changes in the helical structure of the heart muscle can indicate disease long before other symptoms appear. And speaking of the heart, let us talk about something that connects geometry directly to health monitoring. When you get an electrocardiogram, an EG, what the doctors are looking at is a geometric pattern. The P wave, the Kars complex, the T wave. These are all geometric shapes traced by the electrical activity of your heart. A healthy heart produces a very specific geometric pattern. When the geometry of that pattern changes, when the waves become too tall or too short, too wide or too narrow, too close together or too far apart, doctors can diagnose specific conditions. Atrial fibrillation looks different from ventricular tachycardia, which looks different from a heart block. It is all geometry. Doctors are literally reading the geometric signatures of your heart to determine your health. Now let us travel up to the most complex geometric structure known to exist anywhere in the universe. Your brain. The human brain has about 86 billion neurons, each connected to thousands of others, forming a network of geometric complexity that defies comprehension. But let us start with something you can actually see: the surface of the brain. If you have ever seen a picture of a brain, you know it has those distinctive folds and wrinkles. These are called gyri, the ridges, and sulci, the grooves. And they exist for a geometric reason. The cerebral cortex, the outer layer of the brain where most of the complex processing happens, needs to have a very large surface area. But it also needs to fit inside your skull. The solution is the same principle your lungs use: folding. By folding the surface into wrinkles, the brain can pack about 2,500 square centimeters of cortical surface area into a skull that has a volume of about 1,400 cubic centimeters. Without the folding, your skull would need to be enormous, or your brain would need to be much less powerful. The geometry of brain folding is so important that researchers have found correlations between the complexity of brain folding and cognitive ability. More folds, more surface area, more processing power. And within this folded surface, the neurons form geometric networks of staggering complexity. Each neuron has a cell body and branching projections called dendrites that receive signals, and a long projection called an axon that sends signals. The branching pattern of dendrites is, once again, fractal, and the way neurons connect to each other forms a geometric network that researchers study using a branch of mathematics called graph theory. The geometry of these neural networks determines how efficiently your brain processes information, how quickly you can think, and how well different brain regions communicate with each other. Research has shown that disruptions in the geometric organization of neural networks are associated with conditions like schizophrenia, autism, Alzheimer's disease, and depression. Your mental health is, in a very real sense, a reflection of the geometry of your brain. Let me move down to your bones. You might think bones are just solid, rigid structures. But look inside a bone, and you will find something beautiful. Trabecular bone, also called cancellous or spongy bone, has an internal structure that looks like a geometric lattice, a three-dimensional network of thin struts called trabeculae, arranged in patterns that align with the directions of stress the bone experiences. This is not random. The geometry of the trabecular network is optimized to provide maximum strength with minimum material. It is the same principle that engineers use when designing lightweight but strong structures like bridge trusses or aircraft frames. In fact, the geometry of trabecular bone has directly inspired engineering designs. And when this geometry breaks down, when the trabecular network becomes thinner and less organized, that is osteoporosis. Bones become weaker not because the bone material itself has changed, but because the geometry has deteriorated. Osteoporosis is a geometric disease. Even your teeth have remarkable geometry. The enamel on your teeth is made of hydroxyapatite crystals arranged in a geometric pattern called enamel rods, or prisms. These rods are about 4 to 8 micrometers in diameter and extend from the surface of the tooth down to the junction with the underlying dentin. The geometric arrangement of these rods gives tooth enamel its extraordinary hardness, making it the hardest substance in the human body, harder than bone, harder than most metals you encounter in daily life. And the geometry is key. If the rods were arranged differently, enamel would be much weaker. I want you to think about something for a moment. Your body, this thing you live in, this thing that is lying there right now getting more and more relaxed, is a geometric masterpiece. From the double helix of your DNA to the fractal branching of your lungs and blood vessels, from the biconcave discs of your red blood cells to the spiral muscles of your heart, from the folded surface of your brain to the lattice structure of your bones, every part of you is geometry. And when these geometric patterns work correctly, you are healthy. When they are disrupted, disease follows. You are, in the most literal sense, a geometric being. Let that sink in for a moment. Just breathe. Feel your chest rise and fall. That is fractal geometry working in your lungs right now. Feel your heartbeat. That is spiral geometry pumping blood through your fractal circulatory system. Your body is geometry in motion. Now let us leave the body for a while and travel back in time. Way back. Thousands of years back. To the very first civilizations that looked at the world around them and started to see the shapes, the patterns, the geometric order hidden in nature. And what these ancient people accomplished with their understanding of geometry is nothing short of astonishing. Let us start in Mesopotamia, the land between the Tigris and Euphrates rivers, in what is now modern-day Iraq. More than 4,000 years ago, the Babylonians were creating clay tablets inscribed with cuneiform writing. And on these tablets, we find some of the earliest mathematical knowledge in human history. The Babylonians knew about the relationship between the sides of a right triangle, what we call the Pythagorean theorem, at least 1,000 years before Pythagoras was born. There is a famous clay tablet called Plimpton 322, dating to about 1800 BC, that contains a table of Pythagorean triples, sets of three numbers that satisfy the equation a squared plus b squared equals c squared. These include some very large numbers that would have required sophisticated mathematical understanding to generate. The Babylonians were doing serious geometry at a time when many civilizations had not yet developed writing. The Babylonians also gave us something we still use every day without thinking about it. They used a base 60 number system. And this is why we have 360 degrees in a circle, 60 minutes in an hour, and 60 seconds in a minute. 360 is a multiple of 60, and it is also a wonderfully convenient number for geometry because it has so many factors. You can divide 360 evenly by 2, 3, 4, 5, 6, 8, 9, 10, 12, 15, 18, 20, 24, 30, 36, 40, 45, 60, 70, 2, 90, 120, and 180. This makes it incredibly convenient for dividing circles into equal parts, which is exactly what the Babylonians needed for their astronomical observations. Every time you look at a clock or measure an angle in degrees, you are using a system invented by Babylonian geometers over 4,000 years ago. Now let us travel to Egypt. The Nile Valley. Around 2600 BC. This is where we find the most iconic geometric structures in human history. The pyramids. And the Great Pyramid of Giza is the one that really defies belief. This pyramid was built as a tomb for the pharaoh Khufu. It originally stood about 146 meters tall, and each side of the base was about 230 meters long. It was the tallest human-made structure in the world for nearly 4,000 years, until the construction of Lincoln Cathedral in England around 1300 AD. But it is not the size that amazes geometers and engineers. It is the precision. The four sides of the base are aligned to the four cardinal directions: north, south, east, and west, with an accuracy of about 3/60ths of a degree. The base is level to within about 2 centimeters over a distance of 230 meters. The sides of the base differ in length by less than 6 centimeters, meaning the four sides are almost exactly equal. The ratio of the perimeter of the base to the height is approximately 6.28, which is 2 times pi. Whether this was intentional or a coincidence of the construction method is debated, but it suggests the Egyptians had a working approximation of pi. How did they achieve this precision? With geometry. Egyptian surveyors, known as harpedonapti or rope stretchers, used ropes with knots at specific intervals to lay out geometric shapes. A rope with 12 equally spaced knots could be formed into a triangle with sides of 3, 4, and 5 units, which creates a perfect right angle. This is because 3 squared plus 4 squared equals 5 squared, a Pythagorean triple, and this gives exactly 90 degrees at the right angle corner. Using this simple tool, the Egyptians could lay out precise right angles on the ground, which is essential for constructing square bases and aligning structures to the cardinal directions. The Egyptians also had a mathematical document called the Rhind Mathematical Papyrus, dating to about 1650 BC. This papyrus contains 84 mathematical problems and their solutions, including problems involving the geometry of triangles, rectangles, circles, and even the volumes of truncated pyramids. It shows that the Egyptians had a practical, working knowledge of geometry that they applied to architecture, surveying, and agriculture. Their approximation of pi was 256 divided by 81, which works out to about 3.1605. Not as accurate as the modern value of 3.14159, but remarkably good for a civilization working without the tools we take for granted. Now let us cross the Mediterranean to ancient Greece, where geometry became not just a practical tool, but a philosophical pursuit. The Greeks transformed geometry from a collection of useful techniques into a rigorous intellectual discipline. And they did this because they believed geometry was the key to understanding the fundamental nature of reality. The first major Greek geometer was Thales of Miletus, who lived around 600 BC. Thales is often called the first philosopher and the first mathematician. He was the first person known to have used deductive reasoning to prove geometric theorems. Rather than just observing that they seem to be true, he proved that a circle is divided into two equal halves by its diameter, that the base angles of an isosceles triangle are equal, and that vertically opposite angles are equal. These might seem obvious to us, but the revolutionary idea was proving them logically from basic principles rather than just assuming them based on observation. Then came Pythagoras, born around 570 BC. Pythagoras is famous for the theorem that bears his name, that in a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. But the Pythagorean theorem was actually known to the Babylonians and probably the Egyptians long before Pythagoras. What Pythagoras and his followers, the Pythagoreans, contributed was something deeper. They believed that numbers and geometry were the fundamental reality behind all of nature. Everything is number was their motto. They discovered that musical harmony was governed by geometric ratios, that the same mathematical relationships that described shapes also described sounds. This was one of the first great unifying insights in human thought, the idea that different phenomena in nature could be connected through mathematics and geometry. And they were right. As we will see, this idea has only grown stronger over the millennia. The Pythagoreans also discovered something that deeply troubled them: irrational numbers. If you take a square with sides of length 1, the diagonal has a length of the square root of 2. And the Pythagoreans proved that the square root of 2 cannot be expressed as a ratio of two whole numbers. It is an irrational number. Its decimal expansion goes on forever, without repeating. This was philosophically devastating to the Pythagoreans, because it meant that geometry contained quantities that could not be expressed as simple ratios. Legend has it that Hippasus, the Pythagorean who discovered or revealed this fact, was drowned at sea for his betrayal of the group's intellectual secrets. Whether that story is true or not, it illustrates how deeply the ancient Greeks cared about geometric truth. After Pythagoras came Plato, who was so convinced of the importance of geometry that he supposedly had the words "Let no one ignorant of geometry enter here" inscribed above the entrance to his academy in Athens. Plato believed that the physical world we see around us is just a shadow of a deeper reality, a reality of perfect mathematical forms. And among the most perfect forms, in Plato's view, were the 5 regular solids, now known as the Platonic solids. These are the only 3-dimensional shapes where every face is the same regular polygon, every edge is the same length, and every vertex is identical. There are exactly 5 of them: the tetrahedron with 4 triangular faces, the cube with 6 square faces, the octahedron with 8 triangular faces, the dodecahedron with 12 pentagonal faces, and the icosahedron with 20 triangular faces. That is it. 5. No more. No matter how hard you try, you cannot construct a 6th Platonic solid. This is a geometric truth as solid as anything in science. Plato associated each solid with one of the classical elements, the tetrahedron with fire, because it is sharp and pointed, the cube with earth, because it is stable and solid, the octahedron with air, because it feels light, the icosahedron with water, because it is the roundest and flows most easily, and the the dodecahedron with its 12 pentagonal faces Plato associated with the cosmos itself. Perhaps because its 12 faces corresponded to the 12 constellations of the zodiac. This association of geometric forms with the fundamental elements of nature was not just mysticism. It was an early attempt to explain the physical world through geometry. And in some ways, it foreshadowed modern physics, where the properties of fundamental particles are indeed determined by mathematical and geometric symmetries. Then came Euclid, whom we already discussed, who compiled and organized all of Greek geometry into his elements. And after Euclid came more great Greek geometers. Archimedes of Syracuse, who lived in the 3rd century BC, was perhaps the greatest mathematician of antiquity. He used geometry to solve practical problems, calculating the areas and volumes of curved shapes, discovering the principles of the lever and buoyancy, and designing war machines that held off the Roman siege of Syracuse for years. His method of exhaustion, a precursor to integral calculus, used geometric arguments to calculate areas under curves with remarkable precision. And there was Apollonius of Perga, who wrote a comprehensive treatise on conic sections, the curves you get when you slice a cone at different angles. These curves are the circle, the ellipse, the parabola, and the hyperbola. At the time, these were purely theoretical geometric curiosities. But nearly 2,000 years later, Johannes Kepler would discover that planets orbit the sun in ellipses. And even later, the parabola would describe the trajectory of projectiles, and the hyperbola would describe certain spacecraft trajectories. The conic sections that Apollonius studied as abstract geometry turned out to be essential for understanding the motion of objects in space. Ancient Greek geometry, invented for its own sake, became the key to space travel. This is one of the most beautiful examples of how pure geometric knowledge, pursued without any practical application in mind, can turn out to be profoundly useful centuries or millennia later. Now let us look beyond Greece to other ancient civilizations that made remarkable geometric discoveries independently. In ancient India, the Sulba Sutras, written between 800 and 500 BC, contain geometric rules for constructing altars for Vedic rituals. These texts include a statement of the Pythagorean theorem that is independent of and possibly older than the Greek formulation. They also contain methods for constructing squares equal in area to given rectangles, circles, and other shapes, which are essentially geometric solutions to algebraic equations. The Indian mathematician Aryabhata, working around 500 AD, calculated the circumference of the Earth to be about 40,000 kilometers, using geometric and trigonometric methods. This was remarkably close to the actual value, and was achieved centuries before Europeans accepted that the Earth was round. In the Islamic Golden Age, from the 8th to the 14th century, scholars made enormous contributions to geometry. Al-Khwarizmi, whose name gives us the word algorithm, combined algebra and geometry in ways that opened new mathematical horizons. But perhaps the most visually stunning contribution was Islamic geometric art. Because Islamic tradition generally discourages the depiction of living figures in religious contexts, artists turned to geometry to create decoration of extraordinary beauty and complexity. The patterns in mosques, palaces, and manuscripts use intricate geometric tessellations, repeating patterns that tile a surface without gaps or overlaps. The Alhambra Palace in Granada, Spain, built during the Moorish period, contains examples of all 17 possible wallpaper symmetry groups. The 17 distinct ways you can create a repeating pattern on a flat surface. Islamic artists discovered all of them through artistic intuition, centuries before mathematicians formally classified them. And as we will discuss later, some Islamic geometric patterns even anticipated the mathematical concept of quasicrystals by about 500 years. In ancient China, the 9 chapters on the mathematical art, a text compiled over several centuries and finalized around the 1st century AD, contains sophisticated geometric methods including the Chinese proof of the Pythagorean theorem. This proof is visual and elegant, using the rearrangement of geometric shapes to demonstrate the relationship between the squares on the sides of a right triangle. The Chinese mathematician Zhu Chongzhi, working in the 5th century AD, calculated pi to 7 decimal places, a record that would stand for nearly 1,000 years. He did this using geometric methods, calculating the perimeters of polygons with thousands of sides inscribed in and circumscribed around circles. What strikes me about all of this is the universality. Every major civilization on Earth independently discovered and developed geometry. The Babylonians, the Egyptians, the Greeks, the Indians, the Chinese, the Islamic scholars, and many others. They all saw the geometric patterns in the world around them, and they all worked to understand and describe those patterns. Geometry is not a Western invention or an Eastern invention. It is a human invention, or perhaps more accurately, it is a human discovery. The patterns were already there, in the land and the sky and the sea. Humans just opened their eyes and saw them. These ancient civilizations saw geometry as something more than practical mathematics. They saw it as sacred, as a connection between the human world and something greater. And this idea of sacred geometry persists to this day. It is found in religious architecture around the world, in spiritual traditions, in art, and in popular culture. But what does science actually say about it? Let us explore this carefully, honestly, separating what is genuinely remarkable from what is overstated. Sacred geometry is the belief that certain geometric patterns and proportions are fundamental to the creation and structure of the universe, and that these patterns reveal a deep, perhaps divine, order to reality. This belief has existed in virtually every culture and civilization throughout history, and the patterns that are considered sacred are genuinely mathematically interesting. So let us look at them. The most famous is the golden ratio. This is a number, approximately 1.618, usually represented by the Greek letter phi. The golden ratio has a precise mathematical definition. It is the number you get when you divide a line into 2 parts, such that the ratio of the whole line to the longer part equals the ratio of the longer part to the shorter part. This gives you a ratio of approximately 1.6180339 to 1. And this number has some genuinely remarkable mathematical properties. It is closely connected to the Fibonacci sequence, that famous sequence where each number is the sum of the 2 before it. 1, 2, 3, 5, 8, 13, 21, 34, 55, and so on. As you go further in the Fibonacci sequence, the ratio of consecutive numbers gets closer and closer to the golden ratio. 13 divided by 8 is 1.625. 21 divided by 13 is 1.615. 55 divided by 34 is 1.618. It converges beautifully to phi. Now here is where claims about the golden ratio often get exaggerated, and I want to be honest with you about this. You will hear people say that the golden ratio appears everywhere in nature, in the proportions of the human face, in the spirals of shells, in the Parthenon, in paintings by Leonardo da Vinci. And some of these claims are true, some are partially true, and some are simply wrong. Let us start with what is genuinely true. The golden ratio and Fibonacci numbers do appear in the arrangement of leaves, seeds, and petals in many plants. Sunflowers, for example, have spiral patterns in their seed heads. If you count the spirals going clockwise and counterclockwise, you typically get 2 consecutive Fibonacci numbers, like 34 and 55, or 55 and 89. Pine cones, pineapples, and many flowers show similar Fibonacci patterns. This is not mystical. There is a well-understood mathematical reason for it. As a plant grows and produces new leaves or seeds, each new element emerges at an angle from the previous one. If that angle is related to the golden ratio, then the resulting arrangement maximizes the packing efficiency. Each seed or leaf gets the most possible space and sunlight. Evolution selected for this geometry because it is optimal. The nautilus shell is often cited as a perfect example of the golden spiral, but this is partially overstated. The nautilus shell does grow in a logarithmic spiral, and this spiral is indeed beautiful and mathematical, but its proportions do not precisely match the golden ratio. The shell's spiral ratio is typically closer to 1.33 than 1.618. It is still a logarithmic spiral. It is still mathematically elegant, but it is not actually a golden spiral. This is an example of a real geometric phenomenon being slightly misrepresented to fit a narrative. As for the human face and body, the claims are mixed. There is some evidence that people find faces more attractive when they have certain proportions that are close to the golden ratio, but the research is not conclusive. The idea that the ideal human face perfectly embodies the golden ratio is an oversimplification. Human faces are far too variable and complex to be reduced to a single mathematical ratio. What is more solidly supported by research is that we find symmetry attractive, which makes evolutionary sense, because symmetry is often a signal of health and genetic fitness. And the Parthenon? The claim that its facade was designed to fit a golden rectangle is almost certainly false. When you actually measure the Parthenon precisely, its proportions do not match the golden ratio very closely. The claim seems to have originated in the 19th century and has been repeated uncritically ever since. This does not diminish the Parthenon's magnificent architecture. But it is important to be accurate about what is real and what is myth. Now, another pattern central to sacred geometry is the flower of life. This is a pattern of overlapping circles arranged in a hexagonal grid, creating a flower-like design. It is found in ancient art and architecture around the world, from the Temple of Osiris in Egypt to Chinese temples to Leonardo da Vinci's notebooks. Enthusiasts of sacred geometry claim that this pattern is a fundamental template for the creation of the universe. What can we say about this scientifically? The flower of life is a natural result of circle packing, one of the most basic operations in geometry. If you start with one circle and then add circles of the same size around it, each one touching the original circle and its neighbors, you get the beginning of the flower of life pattern. It is mathematically interesting because it contains within it the shapes of the 5 Platonic solids, a pattern known as Metatron's cube. This is a genuine geometric fact, and it is genuinely elegant. But the claim that it represents a divine blueprint for the universe is a philosophical or spiritual belief, not a scientific conclusion. The Sri Yantra, from Hindu tradition, is another fascinating sacred geometric pattern. It consists of 9 interlocking triangles centered around a point, creating a complex pattern of 43 smaller triangles. The geometry of the Sri Yantra is genuinely remarkable. Computer analysis has shown that constructing a perfectly accurate Sri Yantra is extremely difficult because all the intersections must be exact, and small errors in one triangle propagate through the entire figure. The precision required suggests sophisticated geometric knowledge on the part of its ancient creators. So where does this leave us with sacred geometry? I think the honest answer is this. The geometric patterns that people call sacred are genuinely mathematically beautiful and fascinating. They do appear in nature. They do have interesting mathematical properties. But the leap from mathematically interesting to proof of a divine blueprint is not a scientific conclusion. It is a philosophical or spiritual interpretation. And that is a crucial distinction. Science can tell us that these patterns exist and describe their properties. It cannot tell us whether they are evidence of a conscious creator. But here's what science can tell us, and this is where it gets really relevant for tonight. Geometric patterns have a profound effect on your brain. Research by Richard Taylor at the University of Oregon has shown that exposure to fractal patterns, which are patterns that repeat at different scales, reduces physiological stress. Mid-range fractals, those with a fractal dimension between about 1.3 and 1.5, can reduce stress by up to 60%, as measured by skin conductance and other physiological indicators. These mid-range fractals are exactly the kind of patterns found in natural scenes: tree branches against the sky, ripples on water, clouds drifting by. Your brain evolved in a world filled with these natural geometric patterns, and it finds them deeply soothing. There is a concept in psychology called processing fluency, which refers to how easy it is for your brain to process a piece of information. When something is easy to process, it creates a feeling of pleasure and safety. Geometric patterns, with their regularity and predictability, are high in processing fluency. Your brain can handle them easily, which triggers a relaxation response. This is one reason why geometric art, mandalas, and even the simple act of looking at a tiled floor can feel calming. Your brain is saying, I can understand this pattern, and I do not need to be alert for surprises. And this is directly relevant to what we are doing right now. The slow, methodical exploration of geometric ideas, the regularity and predictability of this kind of content, mimics the geometric patterns that your brain finds soothing. You are not just learning about geometry right now. You are experiencing the calming effect of geometric thinking. The orderly progression of ideas, the logical connections, the sense of everything fitting together. It all tells your brain that the world is orderly, predictable, and safe. And when your brain gets that message, it is more willing to let go and drift into sleep. So sacred geometry may not be sacred in the supernatural sense, but the effect of geometric patterns on your brain and body is very real and very powerful. The ancients who decorated their temples with geometric patterns may not have understood the neuroscience, but they intuitively understood something important. Geometry soothes the human mind. Take a moment to appreciate that. Breathe slowly, in and out. We have covered a lot already, from the inside of your cells to the pyramids of Egypt, from Euclid's postulates to the calming effect of fractals on your brain. And we are just getting started, because now I want to take you into nature, into the forests and fields and oceans and skies, and show you that the geometry we have been talking about is not just in ancient temples and mathematics books. It is absolutely everywhere in the natural world, and it is more beautiful than anything humans have ever created. Why does nature use geometry? This is a profound question, and the answer is both simple and deep. Nature uses geometry because the laws of physics naturally produce geometric forms. When forces act on matter, when energy flows through systems, when organisms evolve to survive and reproduce, geometry emerges as the inevitable result. Nature does not sit down with a compass and straightedge and design a snowflake. But the molecular properties of water, combined with the physics of crystallization, produce hexagonal symmetry automatically. Nature does not calculate the Fibonacci sequence to arrange sunflower seeds, but the growth dynamics of the sunflower, governed by hormones and physics, naturally produce a Fibonacci pattern, because it is the most efficient arrangement. Geometry in nature is not designed. It is emergent. It arises from simple rules operating repeatedly over time. And somehow, the results are staggeringly beautiful. Let us start with the hexagon. Nature absolutely loves hexagons, and there is a good mathematical reason for this. The hexagon is the most efficient shape for dividing a surface into equal areas with the minimum total perimeter. Imagine you need to divide a flat surface into equal cells. You could use squares, and they would tile the surface without gaps. You could use equilateral triangles, or you could use regular hexagons. Of these three options, hexagons give you the smallest total perimeter, which means the least material needed for the cell walls. This was conjectured for centuries and finally proven rigorously by the mathematician Thomas Hales in 1999. It is called the honeycomb conjecture. And bees figured it out millions of years before Hales. Honeybees build their hives using hexagonal cells made of wax. Each cell is a nearly perfect hexagonal prism, tilted slightly to prevent honey from dripping out. The walls are astonishingly thin, about 0.05 millimeters, yet the structure is remarkably strong. And the hexagonal arrangement means bees use the minimum amount of wax to create the maximum amount of storage space. This is not because bees are doing geometry. It is because natural selection has optimized their behavior over millions of years. And the optimal behavior produces hexagonal geometry. Bees that built less efficient cell shapes wasted resources and were outcompeted by bees that built hexagons. But hexagons in nature go far beyond beehives. Basalt columns, like those at the Giant's Causeway in Northern Ireland, form hexagonal pillars when lava cools and contracts. The cooling creates stress that causes the rock to crack, and the cracks naturally form a hexagonal pattern because that is the most efficient way to relieve the stress, similar to how drying mud cracks into polygonal patterns. Many of these columns are remarkably regular hexagons. Then there is Saturn's hexagon. At the North Pole of Saturn, there is a persistent atmospheric feature shaped like a nearly perfect hexagon. This hexagon is about 30,000 kilometers across, large enough to fit almost 4 Earths inside it. It was first discovered by the Voyager spacecraft in the 1980s and has been observed continuously since. The hexagonal shape is thought to be caused by the interaction of Saturn's jet streams at different latitudes, a fluid dynamics phenomenon that naturally produces hexagonal patterns under certain conditions. A hexagon on a gas giant, 30,000 kilometers wide. Geometry on a planetary scale. And of course, snowflakes. Every snowflake has 6-fold symmetry. 6 arms, 6 sides, hexagonal geometry. Always. This is because of the molecular geometry of water. A water molecule consists of 1 oxygen atom bonded to 2 hydrogen atoms, and the angle between the 2 hydrogen atoms is about 104.5 degrees. When water molecules freeze, they form a crystalline lattice, where each molecule is hydrogen bonded to 4 others in a tetrahedral arrangement. The geometry of this tetrahedral bonding, projected onto a plane, produces hexagonal symmetry. So every snowflake, every single one of the approximately 10 to the power of 24 snowflakes that fall on Earth each year, has hexagonal geometry. and every one is unique, because the precise pattern of branching depends on the exact conditions of temperature and humidity the snowflake encounters as it falls through the atmosphere. The hexagonal symmetry is determined by chemistry and physics, but the specific pattern within that hexagonal framework is determined by the individual snowflake's history. It is like a fingerprint written in ice by the laws of geometry. Now let us talk about spirals. If hexagons are nature's favorite shape, spirals are nature's favorite curve. Spirals appear everywhere, in the arms of galaxies, in the whorls of hurricanes, in the shells of snails, in the arrangement of seeds in a sunflower, in the unfurling of a fern frond, in the horns of rams, in the tusks of narwhals, in the pattern of hair growing on your head. Part 2. The most common natural spiral is the logarithmic spiral, also known as the equiangular spiral. This is a spiral where the angle between the tangent line and the radius is constant at every point. What this means practically is that the spiral looks the same no matter how much you zoom in or out. If you magnify a portion of a logarithmic spiral, it looks identical to the whole spiral. This property of self-similarity is why logarithmic spirals are so common in nature. They represent growth that maintains the same proportions. An organism can grow larger while keeping the same shape, simply by adding material at a constant rate along a logarithmic spiral. This is exactly what happens in a nautilus shell. As the nautilus grows, it adds new chambers to its shell, each one larger than the last, but with the same proportions. The result is a beautiful logarithmic spiral. The spiral patterns in sunflower seed heads are another wonderful example. If you look at a sunflower, you will see that the seeds are arranged in two sets of spirals, one set winding clockwise and the other counterclockwise. Count the number of spirals in each direction and you will almost always get two consecutive Fibonacci numbers, 21 and 34, or 34 and 55, or 55 and 89. This happens because new seeds are produced at the center of the flower head at a constant angular spacing. If that spacing is the golden angle, about 137.5 degrees, which is 360 degrees divided by the golden ratio squared, then the resulting pattern automatically produces Fibonacci spiral counts. And this golden angle spacing ensures that each seed has the maximum space around it. No two seeds end up right on top of each other. It is the most efficient possible packing. Evolution converged on this golden ratio-based geometry because it allows the sunflower to produce the most seeds in the available space. Galaxy spirals are logarithmic spirals too, but for completely different physical reasons. In a spiral galaxy, the spiral arms are density waves, regions of compressed gas and dust where stars are forming. The rotation of the galaxy, combined with the gravitational interactions of its billions of stars, produces a spiral pattern that is maintained over billions of years. It is remarkable that the same mathematical curve, the logarithmic spiral, appears both in a tiny flower and in a structure containing billions of stars. The physical processes are completely different, but the mathematical form is the same. This is one of the deep mysteries and beauties of geometry. The same shapes appear again and again in completely unrelated contexts. Hurricanes are another example. When you see a satellite image of a hurricane, you see a beautiful spiral pattern. This spiral forms because of the interaction between the rotation of the Earth, the Coriolis effect, and the dynamics of the storm's airflow. Air rushes toward the low-pressure center of the storm, but the Coriolis effect deflects it, creating a spiral inflow pattern. The result is a geometric form that looks startlingly similar to a galaxy, even though the physics is completely different. Now I want to spend some time on fractals in nature, because this is one of the most beautiful and important geometric ideas of the last century, and it connects directly to your health and your experience right now. A fractal, at its simplest, is a pattern that is self-similar at different scales. Zoom in on a fractal and you see smaller copies of the larger pattern. Zoom in again, and you see even smaller copies. In theory, this can continue infinitely. In nature, of course, the self-similarity eventually breaks down at some scale, but over a significant range of scales, many natural objects show fractal behavior. The most visually striking natural fractal is probably Romanesco broccoli. If you have ever seen one, you know what I mean. It is a vegetable that looks like it was designed by a mathematician. It has a cone-shaped overall form, and the surface is covered with smaller cones, each of which is covered with even smaller cones. Each small cone is a miniature replica of the whole vegetable. The self-similarity is so precise and so visually obvious that Romanesco broccoli has become the poster child for fractals in nature. Ferns are another beautiful example. Look at a fern frond, and you see a central stem with smaller fronds branching off it. Look at one of those smaller fronds and you see it has an even smaller central stem, with tiny frondlets branching off. Each level of branching looks like a smaller version of the level above. This is fractal self-similarity, and it is a fundamental part of the fern's growth pattern. Trees show fractal branching too. The trunk splits into large branches. Each large branch splits into smaller branches. Each smaller branch splits into even smaller ones, and so on down to the twigs. The branching pattern of a tree is fractal, and interestingly, the specific fractal properties of the branching vary between species. An oak has different fractal characteristics than a birch or a pine, but they are all fractals. River networks, when seen from above, show fractal branching that looks remarkably similar to the branching of trees or the branching of blood vessels. Small streams join to form creeks. Creeks join to form rivers. Rivers join to form larger rivers. The branching pattern is fractal, and the fractal dimension of river networks has been measured and studied extensively by geographers and hydrologists. Interestingly, the fractal dimension of river networks on Earth tends to fall in a narrow range around 1.8 to 2.0, regardless of the specific geology or climate. This suggests that the fractal geometry of river networks is determined by fundamental physical processes of water erosion and flow. Lightning bolts are fractals. When electrical discharge finds its way from a cloud to the ground, it branches and rebranches in a fractal pattern. The branching is random in detail, but fractal in structure, meaning it shows the same statistical properties at different scales. Coastlines are fractals. Mountain ranges are fractals. Clouds are fractals. The distribution of galaxies in the universe may be fractal over certain scales. And as we discussed earlier, your body is full of fractals. Your lungs, your blood vessels, your neurons, the internal structure of your kidneys, the villi in your intestines, even the wrinkling of your brain's surface. All fractal, all self-similar over a range of scales, all beautifully, mathematically, geometric. Let me talk about symmetry in nature for a while. Symmetry is one of the most fundamental geometric concepts, and it appears everywhere in the living world. Most animals have bilateral symmetry, meaning the left side of their body is a mirror image of the right side. This is not just aesthetic. It has functional reasons. Animals that move through a fluid medium, whether it is water or air, need to be symmetric to move in a straight line. An asymmetric fish would swim in circles, An asymmetric bird would fly in spirals. Bilateral symmetry is an engineering requirement for efficient locomotion. But there is a deeper connection between symmetry and health. Research has shown that greater facial and body symmetry is associated with better immune function, fewer developmental problems, and higher genetic quality. This makes evolutionary sense. Symmetry is difficult to achieve during development. Maintaining perfectly symmetric growth requires that both sides of the body follow the genetic blueprint precisely, without disruption from parasites, malnutrition, toxins, or other stresses. An organism that manages to grow symmetrically is demonstrating that it is healthy and genetically robust. This is why we find symmetry attractive. Our brains evolved to use symmetry as a signal of health and fitness in potential mates. When you look at a symmetric face and find it beautiful, your brain is performing a geometric health assessment. Not all organisms use bilateral symmetry, of course. Many flowers and sea creatures use radial symmetry, where the organism looks the same when rotated by a certain angle. A starfish has 5-fold radial symmetry. A jellyfish has radial symmetry around its central axis. Many flowers have radial symmetry, often with 5 or 6-fold patterns. And the specific type of symmetry usually relates to the organism's lifestyle. Sessile organisms, those that do not move, like sea anemones and many flowers, tend to have radial symmetry because they need to interact with their environment equally in all directions. Mobile organisms tend to have bilateral symmetry because they need a front and a back, a top and a bottom. Tessellations, patterns that tile a surface without gaps or overlaps, are another form of geometric beauty in nature. Turtle shells are tessellated with polygonal scutes. Pineapple surfaces show spiral tessellations. Giraffe skin patterns resemble a type of mathematical tessellation called a Voronoi diagram, where the surface is divided into regions based on proximity to a set of seed points. Dried mud cracks into polygonal tessellations. The scales of fish and reptiles tessellate. Everywhere you look in nature, surfaces are divided into geometric patterns. Voronoi diagrams deserve special mention because they are so common in nature. Imagine scattering a handful of seeds on a flat surface. Now, for each seed, define a region consisting of all the points on the surface that are closer to that seed than to any other seed. The boundaries between these regions form a Voronoi diagram. This simple geometric construction produces patterns that look remarkably like many natural structures: giraffe skin, dragonfly wings, the cellular structure of plant tissue, the pattern of territories in bird populations, even the arrangement of galaxies in the universe. The same geometric principle, partitioning space based on proximity, operates at scales from micrometers to megaparsecs. And finally, bubbles. A soap bubble is a perfect sphere, because a sphere has the minimum surface area for a given volume, and surface tension acts to minimize the surface area of the soap film. This is geometry dictated by physics. When multiple bubbles meet, they form junctions where the films meet at angles of exactly 120 degrees. This was described by the physicist Joseph Plateau in the 19th century and is known as Plateau's laws. These same principles govern the formation of cell walls in biological tissues, where surface tension and pressure create geometric partitions between cells. Nature is a geometric masterpiece. From the hexagons of beehives to the spirals of galaxies, from the fractals of coastlines to the symmetry of flowers, geometric patterns pervade the natural world. And all of these patterns emerge from simple physical and biological principles operating over time. No designer is needed. The laws of physics are geometric, and so the products of those laws are geometric. This is perhaps the deepest truth about geometry. It is not something we impose on nature. It is something nature reveals to us. Take another slow breath. In and out. We have journeyed from your body to ancient civilizations to the patterns of nature. Now I want to take you somewhere even more vast, somewhere that will stretch your imagination to its limits. I want to take you into space, because it is in space, in the cosmos, in the unimaginable vastness of the universe, that geometry reaches its most grand and awe-inspiring scale. Let us start with something relatively close to home: the shape of the Earth. You probably know that the Earth is not a perfect sphere. But do you know exactly what shape it is? The Earth is what is called an oblate spheroid. It is slightly flattened at the poles and slightly bulging at the equator. This is because the Earth rotates, and the centrifugal effect of that rotation pushes material outward at the equator. The equatorial diameter of the Earth is about 43 kilometers greater than the polar diameter. 43 kilometers might sound like a lot, but compared to the Earth's total diameter of nearly 12,800 kilometers, it is a tiny deviation. The Earth is actually smoother and more perfectly round, proportionally, than a billiard ball. But that slight bulge matters for things like satellite orbits and GPS accuracy. Now here is a beautiful story about geometry and the Earth. In approximately 240 BC, a man named Eratosthenes, the head librarian at the Great Library of Alexandria, calculated the circumference of the Earth using nothing more than geometry. He knew that on the summer solstice, the sun was directly overhead in the city of Syene, modern-day Aswan, in southern Egypt. At the same time in Alexandria, about 800 kilometers to the north, the sun cast a shadow. By measuring the angle of that shadow, Eratosthenes determined that Alexandria was about 7.2 degrees north of Syene, as measured from the center of the Earth. Since 7.2 degrees is 1/50th of a full 360-degree circle, the circumference of the Earth must be about 50 times the distance from Alexandria to Syene. His calculation gave a circumference of approximately 40,000 kilometers. The actual circumference is 40,075 kilometers. He was off by less than 1%. With a stick and geometry. Over 2,200 years ago. This is the power of geometry. With the simplest of tools and the right geometric reasoning, you can measure the world. Now let us go from the shape of the Earth to the shapes of orbits. For most of human history, people assumed that the planets moved in perfect circles. Circles were considered the most perfect geometric shape, and it seemed only fitting that the heavenly bodies should move in perfect geometric paths. But in the early 1600s, a German astronomer named Johannes Kepler, working with the incredibly precise observational data of the Danish astronomer Tycho Brahe, discovered that planetary orbits are not circles. They are ellipses. An ellipse is a geometric shape that looks like a stretched circle. It has two focal points, and every point on the ellipse has the same total distance to both focal points. Kepler discovered that each planet orbits the Sun in an ellipse with the Sun at one of the two focal points. This was his first law of planetary motion. His second law states that a line connecting a planet to the Sun sweeps out equal areas in equal times. This means that planets move faster when they are closer to the Sun and slower when they are farther away, in a very precise geometric way. His third law relates the size of the orbit to the time it takes to complete. Specifically, the square of the orbital period is proportional to the cube of the semi-major axis of the ellipse. These three laws are pure geometry. They describe the shapes and motions of orbits using geometric relationships. And they connected directly to the work of Apollonius, who had studied ellipses nearly 2,000 years earlier as abstract mathematical curiosities. The geometry that Apollonius explored for its own sake turned out to describe the actual motion of planets through space. This is one of the most remarkable things about mathematics in general and geometry in particular. Abstract geometric concepts developed in one era can turn out to be essential for understanding the real world in a completely different era. The universe seems to be built on geometric principles that we can discover. About 50 years after Kepler, Isaac Newton showed why orbits are ellipses. His law of universal gravitation, combined with his laws of motion, mathematically demonstrates that any object moving under the influence of gravity will follow a path that is one of the conic sections: a circle, an ellipse, a parabola, or a hyperbola. Planets in bound orbits follow ellipses. Comets that return periodically follow elongated ellipses. Objects that pass through the solar system once and never return follow parabolas or hyperbolas. The geometry of the orbit is determined by the object's energy and angular momentum. Newton unified the geometry of orbits with the physics of gravity, showing that the beautiful geometric shapes Kepler had discovered were the inevitable consequence of the law of gravitation. Now let us talk about how we measure distances in space, because this is another beautiful application of geometry. How do you measure the distance to a star that is trillions of kilometers away? You cannot stretch a measuring tape. You cannot bounce a signal off it and time the return, at least not for distant stars. So how? Geometry, the method is called parallax, and it uses the same principle that your brain uses for depth perception. Hold your finger in front of your face and close one eye. Now open that eye and close the other. Your finger appears to shift position against the background. This apparent shift is called parallax, and it is caused by the fact that your two eyes are in slightly different positions. The amount of shift depends on how far away your finger is. The closer it is, the more it shifts. If you know the distance between your eyes and you measure the angle of the shift, you can calculate the distance to your finger using basic trigonometry, which is just a branch of geometry. Astronomers use the same principle, but instead of two eyes separated by a few centimeters, they use two positions of the Earth in its orbit around the Sun, separated by about 300 million kilometers. They observe a nearby star at one time, then observe it again 6 months later when the Earth is on the opposite side of its orbit. The apparent shift of the star against the distant background stars is the stellar parallax. And from this tiny angle, using geometry, they can calculate the distance to the star. The parallax angles of even the nearest stars are incredibly small. The nearest star system, Alpha Centauri, has a parallax of about 0.768 arcseconds. An arcsecond is 1/3600th of a degree. To visualize how small this is, imagine holding a coin about 4 kilometers away. The angle it subtends would be about 1 arcsecond. The fact that astronomers can measure angles this small is a testament to the precision of modern telescopes and the power of geometric methods. The unit of distance called a parsec is actually defined in terms of parallax geometry. A parsec is the distance at which a star would have a parallax of exactly 1 arcsecond. It works out to about 3.26 light years, or about 31 trillion kilometers. The word parsec comes from parallax and arcsecond. It is a unit of distance that is fundamentally geometric in its definition. For stars too far away for parallax to work, astronomers use other geometric methods, Standard candles, objects of known brightness, can be used to calculate distance using the inverse square law, which is a geometric relationship describing how light spreads out in three-dimensional space. Cepheid variable stars, Type 1 supernovae, and other distance indicators all rely on combining geometric principles with physical observations. The entire cosmic distance ladder, the chain of methods used to measure distances from nearby stars to the most distant galaxies, is built on geometry. Now let us go deeper, much deeper, into the geometry of spacetime itself. Because in 1915, Albert Einstein published his general theory of relativity, and in doing so, he revealed that geometry is not just a tool we use to describe the universe. Geometry is the universe. Before Einstein, people thought of space as a fixed, rigid stage on which events happen. Space was Euclidean, flat, and unchanging. Geometry was something that existed in space. Einstein showed that this is wrong. Space and time are not separate. They are woven together into a four-dimensional fabric called spacetime. And this fabric is not flat and rigid. It is flexible. It can bend, stretch, and warp. And what causes spacetime to warp? Mass and energy. The presence of a massive object like a star or a planet causes the spacetime around it to curve. And this curvature is what we experience as gravity. This is worth pausing on, because it is one of the most profound ideas in all of science. Gravity is not a force pulling objects together. Gravity is the curvature of space-time geometry. When the Earth orbits the Sun, it is not being pulled by an invisible force. It is following the straightest possible path through curved space-time. That straightest possible path is called a geodesic. In flat space-time, a geodesic is a straight line. In curved space-time, a geodesic can be a curve. The Earth follows a nearly circular geodesic through the space-time curved by the Sun's mass. What looks like a force is actually geometry. You have probably heard the analogy of a heavy bowling ball sitting on a stretched rubber sheet, creating a depression. And then a marble rolling along the curved surface follows a curved path around the bowling ball. This analogy is helpful, but imperfect, because it suggests that the curvature is only in 2 dimensions of space, while in reality, spacetime is 4-dimensional and the curvature involves time as well as space. But the basic idea is right. Mass tells spacetime how to curve, and curved spacetime tells objects how to move. And this relationship is described by Einstein's field equations, which are fundamentally geometric equations. They relate the curvature of spacetime, described by a mathematical object called the Einstein tensor, to the distribution of mass and energy, described by the stress-energy tensor. General relativity is not just a theory that uses geometry. It is a theory of geometry. The geometry of spacetime. This has real, measurable consequences. One of the most dramatic is gravitational lensing. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the curvature of spacetime around the cluster bends the light's path. The massive object acts like a geometric lens, distorting and magnifying the image of the distant galaxy. Astronomers have observed this effect many times, and it has even been used to detect dark matter, because dark matter curves spacetime just like visible matter does, and this curvature can be detected through the lensing of background light. Another consequence affects you personally, every day, whether you know it or not. The Global Positioning System, GPS, depends on signals from satellites orbiting the Earth at an altitude of about 20,000 kilometers. General relativity predicts that clocks in the satellites run faster than clocks on the ground, because the spacetime curvature is weaker at higher altitude. The difference is small, about 45 microseconds per day. But if this geometric effect were not accounted for in the GP's software, the position calculations would drift by about 10 kilometers per day. Within a week, your GPS would be useless. Every time you use GPS, whether to navigate to a restaurant or to find your way home, the software is correcting for the geometry of curved spacetime. You are a beneficiary of Einstein's geometric theory of gravity dozens of times a day. Now let us ask one of the biggest questions in all of cosmology. What is the shape of the universe? This is a geometric question, and it turns out that there are exactly 3 possibilities depending on the overall curvature of space. If space has positive curvature, like the surface of a sphere, then the universe is finite but unbounded. You could travel in a straight line forever and eventually come back to where you started, just like walking in a straight line on the Earth's surface eventually brings you back to your starting point. In positively curved space, parallel lines eventually converge and meet. Triangles have angles that add up to more than 180 degrees. If space has 0 curvature, it is flat in the Euclidean sense. The universe could be infinite, extending forever in all directions. Parallel lines stay parallel forever. Triangles have angles that add up to exactly 180 degrees. This is the geometry Euclid described. If space has negative curvature, like the surface of a saddle or a Pringle chip, the universe is also infinite, but with different geometric properties. Parallel lines diverge, moving farther and farther apart. Triangles have angles that add up to less than 180 degrees. So which is it? Astronomers have measured the curvature of the universe using the cosmic microwave background radiation, the faint afterglow of the Big Bang that permeates all of space. The satellite missions MAP, launched in 2001, and Planck, launched in 2009, measured tiny temperature fluctuations in this radiation with extraordinary precision. The size of these fluctuations depends on the geometry of the universe, because the geometry determines how light has traveled across the universe since the Big Bang. And the measurements show that the universe is flat, or at least it is so close to flat that any curvature is too small to detect. This is a remarkable result. A flat universe means that the total energy of the universe might be exactly 0, with the positive energy of matter perfectly balanced by the negative energy of gravity. It also means that the universe might be infinite. We can only observe a region about 93 billion light-years across, because that is as far as light has had time to travel since the Big Bang. But if the universe is truly flat, it could extend infinitely beyond what we can see. The geometry of the cosmos, determined by measurements of microwave radiation, tells us something extraordinary about the nature of reality.